All right, we're going to look at a section 11.3, the randomized block design. There's an accompanying Excel spreadsheet to go along with the lesson with 4 different tabs, and I'll make reference to each tab you need to be on for where we're at in the problem. For now, I'm just going to explain the idea, and we talked about this a little bit as we ended class the other day. So a randomized block design is still a one-way analysis of variance, or we're going to use a one-way analysis of variance to analyze the experiment, except the design of the experiment is no longer a completely randomized design. It is what's called a randomized block design. And a block provides stability into a problem. So the example we had last class was measuring the miles per gallon that a car gets based on a type of gasoline. You might want to employ a block of drivers, so the same drivers are using the cars, so we get more accurate results. We don't, if we don't use blocks, we run the risk of concealing true differences. So a block is a block of something, depending on the context of the problem, that's inserted into the problem to provide stability. And at the end, you can not only analyze the factor, but also the blocks. So what I'd like you to do is refer to the first tab of the spreadsheet for this video. And you want to be looking, the first tab, you should be seeing the production methods and machine operators. And we're going to go through that now. And the reason this is a block design, this context of this problem is we're measuring the production methods of cardboard boxes, and do different methods result in different amount of errors per production run. So there's 4 different ways to manufacture these cardboard boxes. Do the different methods result in a different amount of defects per production run? Because the goal should be to minimize defects. The factor is the production method, and there's 4 levels. So P would be equal to 4, and the response variable is the number of defects per manufacturing run. However, the manufacturing process involves a supervisor, and if we don't use a block, we run the risk of production method 1 having a high amount of errors or a high amount of defects, but it could be because of the supervisors, where production 2 might have few defects, but it's because the supervisor over method 2 is very good at his job. So we would actually find that we're discovering information about our supervisors and not our production methods. So what we're going to do is have 3 different supervisors that operate each production method one time. So there are 4 production method and 3 blocks. So you could say that P still represents the treatment, or P still represents the levels of the factor. And we're going to have B now. So B represents the blocks. We have 4 production methods and 3 supervisors. A little bit more I want to say just about the notation. So in the previous example in last Thursday's class, a treatment was an assignment to a measurement. In this case, a treatment would be a production method and the supervisor in that test run. So the notation, if you're looking at the spreadsheet, the notation X, 1, 1. So the spreadsheet has that as 9. So this is production method 1 under supervisor 1, and they had 9 defects. You can see this in the table in the Excel spreadsheet. Just to become comfortable with it, we have X, 2, 1. So production method 2 with supervisor 1, that had 8 defects. I pick a couple more random ones. So X just represents a measurement. So this is the number of defects for production method 3 when supervisor 2 was operating it, and that is 11. Some other notation. X bar 1 with the dot. So this dot means, well, this representation indicates the average for production method 1 for all of the supervisors, all of the blocks. And 10.3. And you can see these values in the table, and it goes on. So X2 dot is the average for production method 2, which would be 10.3. Production method 3 has an average of 5. Production method 4 has an average of 4.667, and that goes on. We also have notation to represent the average of the blocks. So these are the averages of the levels to the factor. So production method 1, average that many errors. Production method 2, average that many errors, and so on. This notation represents the average for block 1. So this would be the average of column 1 on your spreadsheet is 6. So machine operator 1 had 6 errors. Machine operator 2 had 7, on average 7.75 errors. Machine operator 3 on average had 9 errors. Okay, so this is just the notation. We have an average for each production method, an average for each supervisor. We also have the total average in the problem, just the average of every measurement, all 12, which is 7.583. And that's just the notation to be mindful of. What I'm going to do now is, before we finish solving this problem, I'm going to take a step back and go over some of the longer formulas that we, similar to last class, to illustrate how we, or the reasoning and the methodology about how to solve this problem. So just like last class, we had a total variation in the problem, and then we partitioned that variation into variation due to the treatments and then error. So similarly, we have total variation in our problem, and we're going to partition it. And we're going to have variation due to the treatments or due to the factor. So that's SST. So this is variation in the defects per production run based on the different production methods. What I'm going to introduce new to you now is SSB, the sum of squares for your blocks. So this is the variation in your problem due to the blocks. In the problem we're talking about, that is the variation due to the machine operators. And then we still have SSE, which is the error variation, or the variation in the problem that we haven't accounted for. So because it's a block design, we've got total variation that we can partition into 3 groups, 3 categories. The variation due to the factor, which is the production methods. The variation due to the blocks, which is the supervisors. And then the variation out there that's just unknown, it's error, we haven't accounted for. And there's some longer formulas for these. So because it's a randomized block design, the formula is going to be different than the SST formula you had before. So SST is going to be B times So SST is equal to B, the number of blocks, times the sum of each factor average minus the average of the whole problem squared. The variation in the blocks can be found by doing P times So that is the average for each block minus the average of the problem square. Add them up. And then it's actually much more efficient. We can find the total variation in the problem, and because we have this value and that value, we can find this, subtract this and this, and be left with SSE. So the total variation in the problem is over every measurement which simply means take every measurement in the problem, subtract from it the average of the whole problem, square it and add it up, and that's your sum of squares. Okay, and then now that I have this, this, and this, I could do total variation minus this, and that would leave me with SSE. So that's how you would find it by hand. Luckily, I won't ask you to do that because we were introduced to the outputs. But those are where the formulas come from. Sorry, the lights went out. I fixed it. All right, so we have SST, SSB, and SSE. We were able to find, but just like the previous problem, we have to be mindful that these came from 12 observations. If you look at the table in the spreadsheet, we calculated these values based on 12 observations. So we have to account for that fact, and we need to estimate what would SST be for the whole population. And we find that by doing SST divided by its degrees of freedom, which is P minus 1. MSB is SSB divided by B minus 1. And then MSE is equal to SSE divided by P minus 1 times B minus 1. So that's how you would estimate the values for the population based on the sample data, and you divide each of them by their degrees of freedom. Okay, so the other thing I want to mention before we solve the last problem, or before we solve the problem that we're working on, is, in a general sense, what can we solve in a randomized block design? Okay, so because of this setup, these are what the hypotheses would look like, but all we're saying, we can, just like the previous class on Thursday, we can test for the differences in the blocks. The differences in the factors, so we can test for the differences in production methods. We would say, are they all equal, or do at least two of them differ? You would solve this by finding a test statistic, which is MST over MSE, and you would get that test statistic, and you would compare it to F alpha with P minus 1, and then Those are your degrees of freedom. So you would calculate your test statistic, MST over MSE, compare it to F alpha, degrees of freedom 1, P minus 1, degrees of freedom 2, P minus 1 times B minus 1. Also, the benefit of having a randomized block design is you can also go back and test, are there differences in the blocks? In our case, are there differences in the capabilities of the production supervisors? Are they all equal in terms of the defects they end up on the boxes produced, or do at least two of them differ? The test statistic would be MSB, because that's the variation in the blocks, over MSE, and you would compare that to F alpha, degrees of freedom 1 is B minus 1, and then degrees of freedom 2 is P minus 1 times B minus 1. Okay. So that is everything in a general sense. What I'd like to do is return to the problem we started and solve it. So if you go back to our problem, again, we're comparing 4 different production methods, and we have employed 3 blocks, 3 production supervisors to stabilize the experiment and get more control. So to recap, we have 4 levels to the factor and 3 blocks. If you go to the output now, so this is the second tab of the Excel spreadsheet. First question, well, let's just look at the output first. You'll see the top is summary statistics. It breaks down things. You can see the summary statistics, but what's important to us is the ANOVA table, the bottom portion. So the sources of variation, there's rows, column, and error. We need to go back to the spreadsheet and look at how it was arranged in Excel. Because the machine operators are arranged as columns and there are blocks, on the spreadsheet you're looking at, columns represents the blocks and rows are the production methods, which represent our factor. So we have SST, SSB, SSE, all in our table. If you add them up, you'll get the total variation. The next column gives you the degrees of freedom. So 3 is P minus 1, columns is B minus 1, and then B minus 1 times P minus 1 is the 6. It also gives you the MST, MSB, and MSE. I'm not going to write them out, but you can see MST is the 47.43, MSB is the 9.0833, and then MSE is 0.638889. And then we're given F statistics, P values, and critical values. So the first question is, are there differences between the production methods? Do the different production methods result in a different amount of defects per production run? And you could do 2 things. You could compare the test statistic, 47.43, to the critical value, 4.75. Because the test statistic is greater than the critical value, you can reject the null hypothesis. You can also use the p-value, which is very small, 0.001426, compared to solving this problem at an 0.05 level of significance. That's my p-value. That's my alpha level. Because the p-value is less than alpha, I can reject the null hypothesis. So the null hypothesis in this case is that all of the production methods are equal. So let me write that out. So the production methods, in terms of the defects they result in per production run, they're all equal versus at least two differ. We have evidence to reject the null hypothesis. We could compare 0.000146 to 0.10 to 0.05 to 0.01 and 0.001, and you would find that this is smaller than 0.001, the smallest level of alpha. So we can also say we have extremely strong evidence to reject the null hypothesis because the p-value. And that's what we talked about the other day in class. Okay, so I'm going to erase some things. Remember, there's two questions that can be asked, though, now. Because of the ANOVA table, I can also test that the blocks, whether they differ or not, on, in terms of their effect on the response variable. So do the different supervisors differ in their ability to produce boxes with defects? That's what we're testing here. You would be looking at the columns because that's how our blocks are entered. I talked about that a few minutes ago. You can look at the test statistics, so the F value 14.21 compared to the critical value 5.14. Test statistic is greater than the critical value. These are coming from the table, the ANOVA table. We can also look at the p-value, 0.00529 versus, we'll say alpha is 0.05. The p-value is less than alpha, so we can reject the null hypothesis. The null hypothesis says that the different production supervisors all average the same amount of defects, so we would conclude that at least two of them differ. How much evidence do we have? If you compare the p-value, it's less than 0.01, the third lowest level of significance, but not 0.001, so we have very strong evidence. Okay. What you could do, but we're not going to spend time on, is you would then go and do confidence intervals to figure out, well, which production method minimizes errors and which supervisor minimizes errors. Okay. What we're going to do now is go to the third tab and we're going to look at a different problem. So we'll do one more example to demonstrate how this works, the randomized block design. So the problem we're going to do is the third tab on the spreadsheet, and it is comparing different bottle designs at supermarkets. So, well, let me explain the context. We're comparing do different designs of a bottle result in different sales. So maybe it's laundry detergent. Does the bottle design A versus bottle design B versus bottle design C? Does one appeal to customers more and result in more sales? So we're comparing three bottle designs, A, B, and C. The response variable is the sales. But because it might affect the sales, which supermarket or which store we're selling these bottle designs in, we're going to use a block of locations because bottle A might have high sales, but it could be in an area that's highly populated, whereas bottle C could be in a more rural area that maybe doesn't have as many customers. So to avoid that misleading information, we're going to have a block of 4 supermarkets where we sell all of the bottles. And then you can see the measurements in the table. So bottle A at Supermarket 1 sold 16. I'm just randomly picking places. So C at 3, at 8. But we can see, so bottle design C at Supermarket 3 sold 8 bottles. And the data is all in the table in the spreadsheet. And normally you'd have a problem to read and you would be able to figure all of this stuff out from reading the problem, but I'm just presenting you with the data in the spreadsheet and kind of doing it a little bit quicker. But then you see, after the table, you're told to perform a hypothesis test to determine if the different bottle designs result in different sales and state how much evidence there is to support your result. So I'm asking you to determine if the different bottle designs result in different sales. So we have bottle design A. Is that equal to B? So the question is asking you to determine if the different bottle designs result in different sales. So the average sales for A equal to sales for bottle design B and C, or do at least 2 of them differ? And we can refer to the output to find out the information we need, and we also need to state how much evidence we have. So remember, in this case, if you look at the spreadsheet, the bottle designs, which is your factor, are arranged in columns. So you want to be looking at the columns. And you'll see that the test statistic is incredibly high at 959, which is definitely greater than the critical value of 5.14. The p-value is very small, so that 3.03104 e to the negative 08, the e to the negative 08 means you move the decimal over 8 places to the left, so we really have something like this as the p-value. Definitely less than 0.05, it's less than 0.001 as well, so we would have extremely strong evidence to reject the null hypothesis. I can conclude that at least 2 of the bottle designs differ. You would then go on to see, well, which bottle design maximizes sales. Second question. Was it reasonable to employ a randomized block design? What this question is asking you, was it reasonable to use different blocks? Was it reasonable to do these sales in different supermarkets? And it would be reasonable if the sales potentials of the 4 supermarkets differed. So I'm really asking you to test whether the blocks are the same or they're not. So I'm really saying, does the sales in store 1, is it equal to the average sales in store 2 and 3 and 4, or at least 2 of them differ? Because the blocks are arranged in rows, that's where we want to look on the ANOVA table. Test statistic is very high, 460. It is definitely greater than critical value of 4.75. The p-value, very low. So in this case, we also have extremely strong evidence to reject the null hypothesis and conclude that the different stores have different sales potential. And again, we're not going to spend time on identifying which store maximizes sales, but we're able to at least determine through this experiment that they do have different sales potentials. So that is the randomized block design. Homework 11.1.3, 11.1.5 A and B, 11.1.7 A and B. The test 11.1.2, 11.1.8a. These test problems will be due on your last test of the year. So the test I mentioned last Thursday does not cover this stuff. But you can begin working on these for the final test that will be due at the end of the year. But that is what we're going to cover for randomized block design. It is a one-way ANOVA. We're looking at one factor, but we're utilizing a block of something. It's supervisors, it's supermarkets, to help stabilize the experiment. We gain more control, and then we can also do an analysis on the blocks. Okay? So the next video will be on a two-way ANOVA.